isosceles and equilateral triangles. So the first thing we need to do is talk about what is an isosceles triangle. An isosceles triangle has at least two congruent sides. You can have more than two congruent sides and still be isosceles. So let me draw a picture. This is the most common way that we think about isosceles triangles with two long sides, and those are congruent. We call those congruent sides legs. So that's a leg, and that's a leg. The other side is the base. Up here where the two legs meet is the vertex. And then this would be the vertex angle. And these are base angles. So we have two congruent legs, we have two base angles, a vertex angle, base, etc. So when you see drawings of isosceles triangles, when you get a description of isosceles triangles, this is what the description is they're just going to use this vocabulary. All right, our theorem. We've been using this theorem when we do angle puzzles, but we're kind of going to make it official now. Isosceles triangle theorem. So our theorem is if two sides of a triangle are congruent, then the angles opposite them are congruent also. So what we're saying here is if we have an isosceles triangle, I kind of think of it visually. If those are congruent, then I can draw little arrows here, then these angles are congruent. And if I call this ACB, we're saying if segment AC is congruent to segment CB, then angle A is congruent to angle B. We know the two sides of a triangle are congruent. The two opposite angles have to be congruent. And the converse is true also. Remember, the converse just means we go the other direction. The converse says if we know the two angles are congruent, then the two opposite sides have to be congruent. So if two angles of a triangle are congruent, then the opposite sides are congruent. And I think of this kind of in reverse of that, of the original theorem. So if we have triangle ACB, and we know that these angles are congruent, then the arrows just go the other direction. If angle A is congruent to angle B, then we know that segment AC is congruent to segment CB. So congruent sides mean congruent angles mean congruent sides. All right, so questions there. We've been using this. The theorem itself, we've used that on angle puzzles before. We can also figure out some additional stuff. We call the additional stuff that we can figure out corollaries. I think of a corollary as a bonus theorem. Once we know a theorem, a corollary is easy to figure out. Our corollary to the Isosceles Triangle theorem tells us that if a line bisects the vertex angle of an isosceles triangle, then it is also the perpendicular bisector of the base. And remember, the upside down T means perpendicular. And what we're saying in pictures is that if we have an isosceles triangle and we bisect this vertex angle, the bisect means cut it in half, like so. Well, this guarantees us that this angle is a 90-degree angle, and our base is bisected also. So we cut the vertex angle of an isosceles triangle in half. We also cut the base in half with that segment, and that line meets the base of the triangle at a 90-degree angle. And all of these things that we've talked about, the isosceles triangle theorem, the converse, and this corollary, comes from using Cpctc. So the first thing we would do with this isosceles triangle is bisect this angle. Well, once we bisect that angle, we know the middle segment is congruent to itself. So we have a side, angle, side, side, angle, side triangle. So we know that all the corresponding parts of the triangle have to be congruent. So the base angles have to be congruent. The two pieces that we cut the base into have to be congruent. So we use Cpctc to show all of these theorems. Split the triangle in half, show that the two halves are congruent, and then we know all the matching parts have to be congruent. These have to be 90-degree angles because they're congruent angles that are also add up to 180 degrees. So if they're the same and they add up to 180, then each one of them has to be 90. All right, so questions on our theorems about isosceles triangles. Well, let's look at a couple of problems, the kinds of problems that you might be asked to solve using isosceles triangles. The first one is kind of the standard problem that has to do with isosceles triangles. So I know those two angles are congruent, and this is 7x minus 10, this side, and the other side is 3x plus 6. And the problem is to find x. Well, if those two angles are congruent, what do we know about the two sides? They're also congruent. So we can say these two things have to be the same. 7x minus 10 has to equal 3x plus 6. And then we just solve for x the way we've done since the beginning of algebra. So we get 4x minus 10 equals 6. Add 10 to both sides. 4x equals 16. Divide both sides by 4, and x equals 4. And we could check by plugging in x equals 4 into each of those expressions. And they should come out the same. Questions there? Okay, let's look at another one. Little more going on with this one that we can figure out. I'm going to mark some congruent angles and label some points L, H, G, K, and J. And the first question asks, is segment GK congruent to segment HK, and why? Well, let me highlight those two sides. So there's GK, and there is HK. Well, I'm going to connect with this segment to make a little triangle there, a little red triangle. Well, what do we see is going on with that little red triangle? What about those angles? They're congruent. So that little red triangle is an isosceles triangle. So if it's an isosceles triangle, what does that tell us about these two sides? They have to be congruent. So I would say yes, triangle HGK is isosceles. Second question, is HL congruent to KJ? And same thing, explain if why or why not. Well, here is HL and here's KJ. Are those two blue segments the parts of any isosceles triangle? Are they parts of anything interesting? No, not really. They're part of this trapezoid kind of shape, but we don't really know much about that trapezoid. So we could say we don't know. Not enough information. Last question. How are HK and LJ related? So for these two, we're looking at that segment and that segment. How are those two related? They're both bases, and we have those two angles congruent. We have these two lines. We could think of this as a transversal. So if we're looking at these two green segments as our lines, and this segment going up the side as a transversal, what kind of angles are these two? They're corresponding. Angle L and angle GHK are corresponding angles. And they're congruent. So what does that tell us about those two segments? If corresponding angles are congruent, then the two segments are parallel. HK is parallel to LJ. We'll talk about that thing in triangles in another chapter or two. But we have enough information to decide those two segments are parallel. All right, let's look at one more example, and then we'll talk about equilateral triangles. All right, so in this example, I'm going to say this is point A, BC. This side is 10. This angle is 60 degrees. And this angle is 30 degrees. And we want to find the length of AB. Well, I don't have much information the way that we've drawn it there. Without figuring some stuff out, I don't have much information about segment AB. But what can we figure out? What's easy to figure out? Yeah? Yeah, these two have to make 180 degrees together. So we can figure out this angle inside the triangle. So what does this angle have to be? 120. So we figured out that angle is 120. Now we have two of the angles in a triangle. What do all the angles in a triangle have to add up to? 180. So we have 120 and 30. So together those are 150. What does that leave for this one? 30 degrees. Well, these two angles are the same. So what does that tell us about these two sides? They have to be the same. So this side would be 10. So AB is 10. So we had to use a linear pair, and we had to use triangle sum to figure out that was an isosceles triangle. All right, let's talk about equilateral triangles. And I think we can figure out what we're going to say for our theorem without writing it all out. So there's an equilateral triangle. And we're going to say if a triangle is equilateral, then, well, let's look at these two sides. If we know those two sides are congruent, what do we know about these two angles? They have to be the same. That's an isosceles triangle. So we know that those two angles have to be the same. Well, now let's look at these two sides. These two sides are the same. So what do we know about these two angles? They have to be the same also. So that angle has to be an angle with two tick marks. So we can say if a triangle is equilateral, then it is equiangular. And if all the angles in a triangle have to add up to 180, and in an equilateral triangle they're all the same, what does each one of them have to be? So we need three angles that are exactly the same that add up to 180. So 180 divided by 3 is 60. So the angles in an equilateral triangle are 60 degrees. We can also go the other way. So if we started with all the angles being congruent, and we know that these two angles are congruent, what has to be true about those two sides? They have to be the same, right? And if these two angles are congruent, then these two sides have to be the same. So all the sides have to be the same. So we can say the converse also. If a triangle is equiangular, then it is equilateral. And this comes from the isosceles triangle theorem, because an equilateral triangle is an isosceles triangle. It has at least two congruent sides. All right, questions? Okay. All right, there's that.